Adolfo Ibañez University. So we'll talk about strings and universal structure of ion divergences in nonabelian gauge theory on the celestial sphere. So,
thank you very much, Martin. Thank you very much for the invitation. I know it's cliche, but I really mean it. It's really a pleasure to be here. So thank you very much for everything. Okay, so my talk is pretty much in this area that has been going on for the last maybe even 10 years, more or less. That goes under the name of celestial holography, flat space holography. And in the recent years, people have found connections with this theories called Carolian theories. And there seems to be like a direct map between what people call celestial holography and Carolian holography. But okay, I will not say much about Carol. So my interest in these topics are more related. I know that people work a lot on gravity in flat space holography, well, in holography in general. But this talk will be more focused on how can we use this formalism, all this framework, in order to understand, hopefully, in a different way, the problem of infrared divergences in QFT. Specifically, I will focus more on nonabelian gauge theory. So okay, so this is in collaboration with many of my friends who are there. So this is the outline. Maybe it's too small. Can you see in the back? Okay. So I'll start with some introduction and motivation for flat space holography. In particular, I will focus on what's known as celestial holography. And within this, I will go. This will be the main part of my talk, actually. So this is the main object that I will be focusing on, which is the infrared. The soft collinear factorization of infrared divergences that occur in gauge theories, in abelian gauge theories, but in non-abelian gauge theory, that will be the focus of my talk. And I will show you that this factorization persists at the level of what are known as the celestial amplitudes. So I will make a quick introduction about what celestial amplitudes are. And basically, it's a bunch of Mellin transforms. And usually, well, you don't expect, you take the Mellin or Fourier transform of a product of two functions. The result is not the product of the two transforms, but in this case, it does. And what happens is something related to the renormalization of the hard part of the amplitude. Okay, I will say more about this in a few minutes. And then I will use the large N expansion in non-abelian gauge theory in order to extract more information about this factorization. And so the main goal of I'll go into details now, but the main goal is to look for something universal, and this factorization has this universal factor here. Okay, and this will be important for, okay, just in a few minutes I'll say more about this. And then at the end, if time permitting, I will use the string theory as a toy model to, because of the exponentially soft behavior that string theory amplitudes have in the UV, in the deep UV, that makes string theory amplitudes very apt to study the celestial holography program in that framework. And finally, I'll just mention some work in progress that we're mapping the celestial, the worldsheet sphere, for example, in the case of closed strings. So the worldsheet theory, we're trying to see how can we map this the CFT on the worldsheet to the putative CFT that lives on the boundary of Minkowski or asymptotically flat space, also known as the celestial sphere. So okay, that's basically the outline. I don't know what has this page was intentionally left blank. No. Okay. So the main motivation is this discovery that happened initially in the 60s by BMS, which is this And also in gauge theories, also that also happens, which is the enhancement of the symmetries at infinity, in particular at null infinity. So they were studying radiation, and they realized that the group of asymptotic symmetries of just flat space or asymptotically flat space is not Poincare, but it's an infinitely large. I mean, it's an infinite dimensional group, and this was developed more in depth by Bartnik-Trossard in 2010 and Campiglia-Lara in 2015. So all this was a classical treatment, so just classic GR. But the obvious question is, okay, if they found this an infinite enhancement of symmetries at asymptotic, at infinity, what are the consequences of the symmetries at the quantum mechanical level? And a quantum mechanical object, as we all know, that is well defined. It's actually it's defined at the end of the space-time is the S matrix. So I will talk about the S matrix in the rest of the talk, basically. So from the point of view of holography, this is what people, this is the dream, right? You have some physical theory that lives in 3+1 dimensions, and of course the dream is to find some sort of boundary, that theory that lives on the boundary of asymptotically flat space that would reproduce the physics of the bulk. So flat holography so far is a bottom-up approach. Contrary to ADS-CFT, we have strings and then you go from the top down. This is a bottom-up, and the bottom is the S matrix. Okay, and nowadays, so it started with this celestial holography program, and now which is defined on a 2D sphere. But there's also this other approach called Carolean holography, which is in 3 dimensions, which on top of the 2-dimensional sphere at infinity, you also have the null time coordinate that defines that boundary as well. So that's naturally in 3 dimensions. And there's a one-to-one map between the objects that correlation functions that people compute here are in one-to-one correspondence through just basically a Fourier transform in order to go from here to here and vice versa. Okay, so the S matrix is, you could say, it's a very naive holographic object. You can say that. I mean, it's defined on the boundary of a space-time. So why not looking for as a starting point, start from the S matrix to see what can you say about that putative theory that lives on the boundary. Okay, so here's the Penrose diagram. So I was told that I had to be like pedagogical. So the first part would be very hopefully pedagogical in that sense. So here it goes. This is the Penrose diagram of just Minkowski space. That's the future null infinity. So this is where radiation gets to photons, gravitons, and the future and the past null infinity. It's where the radiation comes from. So the S matrix is basically you prepare a state. Here we call that N. You have massless. I will focus on massless states, in the as external states. That's where the all this framework is most developed so far. So let me just talk about massless particles for now. And so you have massless particles, and okay, something happens, some scattering process, and then you have particles coming out. And then the S matrix is basically the operator that that brings you here, projects this into the evolves this in state into the future, and then at the end of the day, you bracket that evolved state with some out state, and that is what we call the scattering amplitude. Okay. So the main idea of this program is to see if you can get this scattering amplitude in terms of some correlation function, which is only defined, with data on the boundary, and this is usually called a celestial correlator or some correlator that lives on the celestial sphere. So the main question is, okay, what are these operators? What is this actually this correlation function? What is that average, or that you're taking? So in general, is not known. However, there are many recent there are many developments and more recent ones. And for example, for soft, so when you study soft theorems, when you have soft particles, soft gravitons, soft gluons, soft photons, for example, Strominger in 2021 did a computation in which he computed some OPEs of these operators, and then the algebra satisfied by these operators turned out to be this infinite dimensional algebra, W1 plus infinity algebras at tree level. So the hope is that quantum deformations of this algebra will correspond to quantum corrections of the amplitudes, and that's the hope. So loops and central charge as well. I think it's still in a murky ground so far, but those symmetries are there, and this is a new thing that people did not, they were not known before. And up until now, there isn't such a connection yet. That could be people hope that. Hard to say because you are mixing. It's not even an option. That's right. That's right. The Mellin transform that I will write down in one more slide or two more slides actually is an integration over the energies of the external states from 0 to infinity. So you mix all the deep infrared with the deep UV in one single object. So the hierarchy that Gaston was mentioning is somewhat lost in this framework. Okay, I will not say much more about this. I will actually say it in a few more slides. So let me skip that. So okay, if you try to find, if you try to formulate some kind of a holographic duality between what happens in the bulk and what happens at the boundary, the zero order computation that you should do is the matching of the symmetries, for example. So at the initial level, you can use this. Actually, Dirac was the first one who wrote something related to this, that noticed that the four-dimensional Lorentz group is isomorphic to the global conformal group on the Riemann sphere. Okay, so how to take advantage of that? This is how this whole program started, actually. So for the sake of pedagogy, let me write a few things. So the first thing you do is to go into boundary coordinates, which are adapted for null infinity. So if you want to describe the null boundary, you use this change, t plus r, you call it u, and t minus r, you call it v. So for example, I think I did the other way around. This should be v and this should be u. But again, you take the limit when r goes to infinity with v fixed, so that allows you to move along the null boundary of Minkowski. And then instead of using the usual angular variables, it's very convenient to define this complex variable. So z is just I always forget, azimuthal in the other angle, the angle of spherical coordinates. And also, if you include gravity, now you have super translations. I will not say much more about that because I'm not really an expert. Here we have experts in the audience. So you have super translations, which is the BMS group, and you have also super rotations, which is it's an enhancement also of this infinitely large symmetry group that appears at infinity. Then this enhances the global group to the full two-dimensional conformal group. You get Virasoro-like stuff. Okay, so you can say that at the end, celestial amplitudes is just simply a change of basis, but it's a very useful change of basis. So let me review them. So usually one write amplitudes in momentum basis. So you have free states, asymptotically free states. You have, for example, this some plane wave. And now let's parameterize the momenta. I said that I was going to focus on massless states. So this is a very convenient parameterization for massless states. You can check that q squared is equal to 0 for any z. So this is the parameterization that we will use. And this omega basically parameterizes the energy of the particle. Okay, so z just tells you where in the at infinity, in which place on the celestial sphere this photon or the graviton, pierces the sphere infinity, and so that z gives you that location, and omega was the energy carried by the particle. So at the end of the day, basically what you do is this. You have some object here. For example, here it's a plane wave, and you do a Mellin transform over the entire range of energies of the particle. So you have exchanged the energy for this new variable, delta. And as we said before, notice that you're summing, you're mixing all the energies from the deep infrared to the UV. And when you do this, you realize that this object here, for example, transforms precisely as a conformal quasi-primary field with scaling dimension delta. So the parameter here of the Mellin transform actually becomes a scaling dimension. And if you were going to do this with some spin 1 or spin 2 particle, then you will see that here you get actually the h of the conformal weight, and the j that appears in that transformation is actually the helicity of the particle. So just to get more intuition about what these things are, take again the simple case of a free particle, do the Mellin blah blah blah. You can perform that integral very easily. You get this, and then you notice actually that these are boost eigenstates. For example, just pick any direction, take the particle moving along the z-axis, so that would be the momenta, the four momenta of the particle, and then I replace that into here. Okay, so that q was that 1,001. And then if you act, for example, with the generator of a boost, you see that this is actually an eigenfunction of that, and that is the eigenvalue. Okay, so these are boost eigenstates. Okay. So celestial amplitudes are, so you start from you compute some amplitude in momentum space, you use your favorite method, Feynman diagrams, bootstrap, whatever, and then you define this new object. So you integrate, you do this Mellin transform over each of the external legs. So you're exchanging again all these energies for this scaling dimension now, and then you just integrate over all the external, each of the external particles in an endpoint particle amplitude. Oops, sorry about that. Okay, and now you can check, for example, so if the original transformations under Lorentz, this new object, how does it transform? It transforms exactly as a CFT, as a correlation function in a 2D CFT with primary fields, in which that delta is the scaling dimension, and this J, the conformal spin, is actually the helicity of the original particle that you were scattering. Okay, so let me show, for example, okay, so this is what we said before, that you're forced to deal with, the UV and the IR in one framework. So let me give you a bunch of examples. Okay, using that parameterization, if you write the Mandelstam's, you get that. Okay, so these are the product of the two energies, and then the locations on the celestial sphere go into there. And then so after you integrate over all energies, so integrate over all the omegas, you end up with an object that only depends on the z's and also on these scaling dimensions that I had before. So for example, all the Lorentz invariants in the 4D bulk become distances on the sphere. Well, this is we're using this stereographic projection of the sphere into the complex plane. Okay. Okay, so let me give you a quick example. Take, for example, the the foreglown amplitude at tree level. The only one which is non-zero is the what's called the MHV, the maximum helicity violating amplitude. So in that parameterization that I showed you before, it has this form. I will not say much about it, but okay, you do the thing, and then at the end you end up with exactly what we were expecting. You get this 4.2D correlation function, and here you get a conformally invariant factor that has all the information about the actual process, and so it's theory dependent. This is not theory dependent. This is pretty much fixed, of course, by conformal invariance or conformal covariance, and this would be the thing that depends on the cross ratios. I did not put it here, but this R, when you write the Mandelstamm's S and T in terms of the Z's, of the positions on the celestial sphere, that becomes a conformally invariant cross ratio. So that function there depends only on that ratio, and is theory dependent. And you can check these numbers that you get at the end of the day. You get that the spins, the 2D spins, J1 and J2, are precisely the two minus helicities of the incoming particles, and the other ones are +1 and +1 of the outgoing helicities, the helicities of the outgoing particles. Yes? Okay, they're traced, the color, um, um, yeah. That's G. Young-Mills. Yeah.
Your delta, how do you fix it?
That again?
Delta I.
This one?
No, the conformal, yeah.
No, they're not fixed. You see, they're independent parameters.
Okay. But do you fix it in the end, or do you leave it free?
It's free.
Okay.
So at the end of the, so yeah, so maybe I should say more about this. So just take the plane wave, right? Right. So because these particles are external states, their own shell, then of course you have three real numbers specifying, the three momenta, right? Px, Py, and Pz, and the energy is fixed by the on-shell condition. So here we're exchanging, one of those real numbers for this real number here. So the number of degrees of freedom that you have for each particle is still 3. But instead of having now, 3 momentum coordinates, now you have 2 on the celestial sphere and this and this and this delta.
So it depends on the external legs that you want to put.
Say it again?
When you put the external legs, you fix the momentum and you fix delta.
Well, the delta, it's not that you fix the momentum, right? You integrate over all the energies of the external momenta, and the dual variable of the energy is that delta. Yeah? It's like a Fourier transform at the end of the day, right? You exchange momentum. Okay. So, all right. Let me do the 4 graviton case also at tree level. Again, this is the MHV amplitude. So notice that contrary to the previous case, you see that there's no dependence in the energy. Okay, this is basically because Young-Mills is scale invariant in 4 dimensions. So, but gravity, of course, is not, and you see that you have now powers. You have more powers in the numerator than in the denominator. So this is just an indicator. It's just a consequence that gravitational amplitudes, the coupling, runs with. Increases with the scale. So this what it does is that at the end of the day, when you compute this Mellin transforms, this thing will blow up. Okay, this will make it blow up because I did not mention here this delta. I'm sorry, what? Only general relativity. Yes. So I skipped that. I did not mention that these deltas are 1 plus I lambda. Okay, so the real part of this deltas is 1, and then you have an imaginary part. So that one kills that one here. So of course this thing now blows up at high energies. Yes, I will. I will mention this. Spoiler alert. Yeah. So this happens to all gravitational amplitudes in field theory, GR. However, there you go. In string theory, because of the exponentially damped behavior that string amplitudes have in the UV, this softens all these UV divergences. So this make string theory amplitudes very useful to in this framework. Also, there's this famous computation, Doft and Veneziano even. When you have some graviton amplitude and you go at very, very high energy, at Planck energies, at the end of the day, when the process is dominated by black hole creation in the internal states, the amplitude, the 2 to 2 amplitude, it's also exponentially suppressed, and the exponential factor here is basically the black hole entropy, the Wittgenstein-Hawking entropy of a mass similar to the center of mass energy of the scattering process. So that's also a very nice feature of quantum gravity. Okay, so basically, yes.
So that's gluon amplitudes and target amplitudes. They're usually related by double copy.
Yes.
I'm not very.
I mean, yeah. There are some papers about it. I think Casali and Andrea Pum they wrote some initial paper about the double copy in this framework. Yeah, but I'm not very sure. What the consequences of it is, more than just taking the double copy originally and then compute some mega amplitudes. I'm not sure the. Yeah. Okay, so just that very nice feature of quantum gravity at the in the UV, allows you to compute these things more. I mean, all these integrals converge in that sense. Okay, so now let me go into the. So that was the very quick introduction on celestial amplitudes. So let me talk about what's more the focus on this talk, which is the infrared structure of nonabelian gauge theory, seen from the point of view of these celestial amplitudes. So in gauge theories and gravity, Weinberg for QED and gravity, he showed that infrared divergences actually exponentiate, and it's a new universal thing that if you have, for example, any theory coupled to a photon, any matter field coupled to a photon, the infrared divergences will always exponentiate. And on top of that, there's this factorization here in which you have something which is completely infrared safe, which is called the hard part of the amplitude. So if you use dimensional regularization and you send the regulator to 0, this is IR safe, and this will produce all the infrared divergent terms. But the nice thing is that all those divergences actually exponentiate. Okay, and so the soft and the collinear ones. And the nice thing that I think that maybe one of the nicest features of this is that it's universal, in the sense that it does not really depend on the process. And this part depends on the process, of course, the hard part, but the universal one does not depend on the process. So if one is looking for some universal feature of this putative CFT on the celestial sphere that we're looking for, this seems like a good place to look for structure for it. Okay, that's basically what it. Yeah. Okay. So quick example, for example, a simple computation in just massless scalar QED, for example, this is what the exponentiation looks like. This comes from basically just a one loop integral. Here you have Qi, Qj, these are the charges of the electrons or positrons. And all the momenta dependence or all the dependence in the Mendelssohn variables are there in the soft collinear part. And then you have all the rest. Okay, the hard part with the complicated part, of course, but the good thing is that, of course, that's infrared safe, and all the divergences are hidden here. For example, this alpha here is the electric charge log of the infrared cutoff that you put here. You can also write it in dimensional regularization. I just wrote it some cutoff. Same thing with gravity. All the divergence, the infrared divergence is also exponential. The no collinear divergence is in gravity, and it looks pretty much the same. But the only difference is that instead of having the multiplication of the charges, now you have the dot product of the momenta of the gravitons. Okay, and here again, this gamma here is the infrared divergent thing. Okay, so in non-abelian gauge theory, this exponentiation is a lot more complicated, but up until now, uh, it looks like that. And so here we're going to use what's called the Catani-Simo, the color space formalism. But okay, let me just tell you how this object looks like. This Z now is not just a simple exponential. It's an exponential of an integral over energy scales. This is some cutoff scale that okay, defines what you mean by infrared. And the central object here is what's called the cusp anomalous dimension matrix. So this whole thing is a matrix also, because in this formalism, so amplitudes are written instead of just like that. I mean, they're written like in that formalism where you have, so the amplitude is like a vector, it's like a ket, and then the factorization is some matrix times some other ket, and the other ket is what we call the hard amplitude. So again, this is a matrix in this color space, the Catani-Simo formalism, and the amplitudes are vectors in this color space. Okay. The other thing is that this object here is actually infrared finite, and all the divergences are actually produced by doing the integration over these energy scales. Okay. So take any amplitude with external gluons, for example, where you have a color associated some to each of these external states, and because of color conservation, you have this. Actually, this is not exactly true. This is only true in the when it's acting on some amplitude. So because of gauge invariance. But okay, but since we're computing amplitudes, we can always use that inside of some amplitude computation. So again, I want to focus on this object, which is the cusp anomalous dimension matrix. And for gauge theory, so let me say a few things. This is a computation that comes from basically a one loop thing. This is the collinear contribution, but notice that the collinear contribution is proportional to the identity matrix, so it's not really relevant, at least for the purposes that I want to focus on here. And this Ti and Tj, this dot product is in color space. So Ti and Tj corresponds to I and j to two different external gluons, for example. And then you have the log of the Mandelstams there. Then this contribution here appears at 3 loops. And this computation was done by Almeli, and Gardi in 2015, and it was sort of hinted by Karun Ud in 2013. And if you write, so this only depends on this object here, which if you look at it, and if you write these Mandelstams, I'm sorry if you don't see them very well, but these are just ratios of products of Mandelstams. When you use that the momenta parametrization that I mentioned before, it's an SL2C invariant object, which is very helpful for the computations that I'm going to show.
Sorry, just to understand.
Yes.
What was the comment about the Simon? I didn't hear it.
Yeah, I did not want to say much about it because I might not be remembering correctly. But if I remember, was he the one who said that? So people before that computation, before this computation of 2015, there was the hope that maybe it was exact. There were no corrections because
there was a previous conjecture due to Becher and Neubert that there's only this dipole.
That's right. That was the dipole conjecture, right?
The salary that it's incorrect conjecture.
Yes, exactly.
To be incorrect.
That's right.
And indeed, this calculation by showed it very explicitly that this loop
It
exists.
is there, right?
Now for Seymour,
This is
Seymour also did important work on the Ricci limit. So maybe there was some indication from a Ricci argument that there has to be an extra term.
I remember that paper was the actually why the gluon regiases, I think was the name of that paper.
So maybe he had an argument there that has to
Exactly. I think yeah. He had the argument exactly that the three loop term should not be zero, and I think he also predicted that it should depend only on this cross ratios.
Yeah, I mean, I think that follows from the web definition. But maybe he had a Ricci prediction. I don't remember. Thank you.
I mean, I don't remember it very well, but that's why I didn't want to say much about it. But I think it's his prediction was there. All right. So that's the one loop thing. Two loop is zero. Then there's the three loop correction, and you may wonder, okay, what about four loops? And there was a paper by Becker and Neubert in 2019 in which they showed that the four loop correction is actually there. And okay, so I did not write it. I will write it later on because I will focus on this first object first, and then I will say more about these other corrections. But okay, this for loop thing, unlike this, only depends explicitly on the Mandelstam. It does not depend only on these ratios. But the good news, at least from our point of view or our computations, is that it also has a nice celestial interpretation. So we have a nice celestial interpretation for this, for that, and also for that one. And okay, and this Johannes actually, well, I have the reference later on, but Johannes, they did work on this too. Okay, let me actually, it's going to be here. So let me write the Casp anomalous dimension matrix just using this parameterization of the momentum. I mean, people could have done this a long time ago. Let me just plug this there, and then so the Mandelstams, since these are massless particles, so at the end of the day it's just 2pi.pj, and this is how it looks like. So for the moment, let me neglect the for loop correction. And I will also neglect the three loop correction, sorry. Yes. Okay, so when you do that, because of this log, you see that when you plug this Mandelstam Sij, when you plug this Mandelstam here, because of a log, you get a separation of log of the omegas plus log of the z's. And everything here is in the exponent, if you remember. So I have the exponential of something of a sum of two logs that one of those logs depends on the omega plus the log that depends only on the zij's. And that's pretty much everything that it's needed here. So the original thing in terms of the Mandelstam gets separated into two things. Something that only depends on the positions on the celestial sphere, plus something that depends on the logs of these energies. And here also to make it look like this, we also used color conservation, and because of that, and also here appears an identity matrix. Okay, so all the matrix structure is the nonabelian part is there, and this is simply just diagonal part. Okay, so if you plug that exponent into the original soft collinear factor, because of that one, that path order actually becomes immaterial, and the path order only involves now this part here. So now, just using, I'm not doing anything. I'm not doing any Mellin transforms yet. Just change of the parameterization of the momentum. This is how the soft collinear factor looks like. So all the energy dependence becomes that product there. Okay. So now we go celestial. So we perform all these Mellin transforms, and so the original amplitude, which was the soft collinear factor here, which is has information about all loop infrared divergences times the hard part that depends, okay, that's the hard part, that's the rest of the amplitude. And now I do this Mellin transforms. So the factorization that we had before, you see now this object here is invisible to this energy integral, so it comes outside. And now what we had before, which is the integration of these energies with some scaling dimension, you see that the only effect of the infrared divergence is here. This k hat factor here is infrared divergent. So the only effect that it has is just shift the original scaling dimension of the hard part of the amplitude by this by this case it's infinite shift. But you can say now that, okay, now my renormalized scaling dimension of the hard part is now that. Okay, so you just lump everything into the new scaling dimension. And again, as you can see now, this toodles here, these are the Mellin transform amplitudes, also known as the celestial amplitudes, and you see that the factorization persists also in this basis. Okay. Okay, and so what? So now let's go for the other terms. This, because it was only a ratio of energies that you had the same powers of energies in the numerator and the same powers of energy in the denominator. Because of at the end of the day, you use momentum conservation. That thing that does not depend on the energy, so it comes out. So the only factor that enters in the only correction, I mean the new correction that enters into the Mellin transform thing is the for loop thing. And the for loop, if you look at it, is again just only has logs. So again, we have this since it's log of the energy and times and plus log of the positions on the celestial sphere, you can play the same game. And after again doing the Mellin transform, including that factor over there, you get that this for loop correction just simply again renormalizes the previous correction. So at the end of the day, the only effect is just correcting the scaling dimension of the hard part. So if you do all that, then you see that here you get precisely the for loop correction that was computed by Johannes and Bernard Misselberger in 2019. So at the end of the day, you get that the mirror effect of all this. I'm sorry. So Gardi and Magnea there's an argument there that all these loop corrections will keep being just logs of the Mandelstam. So if that's true, then that would mean that all the higher loop corrections, all the infrared quantum effects, simply renormalize this scaling dimension of the hard part of the amplitude. Okay, so the original goal was to find some theory that lives on the boundary of a Minkowski space on the celestial sphere that somehow describes what happens in the bulk. There isn't such a complete thing yet, but maybe we can say something about that theory on the boundary, or some partial part of that theory. Specifically, can we say something about the universal structure? So can I find some Lagrangian, some theory living on the celestial sphere at infinity that captures the information, at least of the universal infrared structure of nonabelian gauge theory? So so we posted this equation. So could we search for a system of equations that describe the universal structure of the theory? So again, let me write down the object once again. So let's see if you can find, but now the object is written, you see, on the celestial sphere only because of the factorization that I previously showed, in which now this does not depend on the mass sum anymore, only on positions on the celestial sphere, and all the infrared divergences acting on the hard part just becomes a renormalized scaling dimension of the celestial hard amplitude. So let's see if we can find some system of equations that maybe satisfy this soft collinear object. And so again, let me remain within this, what, as Johannes said, the dipole approximation. So let me just focus on this term, and I can also focus on this one here because of the identity matrix there. It's basically very innocuous. So let me just keep the first line. So in the large n limit, now I go SUN and I do a 1/n expansion. So in the large n limit, this gluon, the generators of SUN, project actually the hard part onto an amplitude of vectors in color space with single traces only. So at the end of the day, when acting on the hard amplitude, every time, you remember that this is in the path order exponential, blah, blah, blah. And then if you expand that exponential, whenever you see this Ti, Tj acting on the hard part of the amplitude, because of the large n limit, if you just do things at leading order in 1/n, at the end of the day, this is basically what happens. That gets projected into this, just the identity matrix, and the ith gluon with the j gluon sort of interact through this nearest neighbor kind of looking interaction. Okay, and n is over there. Okay, so in that limit, you can compute Zn, the soft collinear factor, explicitly. Because of that identity here, again, the path ordered exponential it's almost trivial. So at the end of the day, you end up with this object here. And for example, if you look at Di Francesco's book, you recognize that this is the partition function for a Coulomb gas. But because of these Kronecker deltas, so I put Coulomb gas in quote unquote, because it's not really a Coulomb gas, but it's a log of the distances between the two particles, but quote unquote because it's only nearest neighbor interactions. Okay, so now you can ask the question: okay, how can I reproduce this correlation function? Yes, everyone against everyone. Yes, yes. But here it's just nearest neighbor. So this is why the quote. But maybe the nice thing is that now, what if you go one order in 1/n, one order extra in the 1/n expansion? Then you start to get not only the nearest neighbor, but a little bit further away and further away in the color decomposition. Okay. So so you can ask the question, okay, how can I reproduce that correlation function? Again, just if you look at the yellow pages, the Di Francesco, or any of these CFT books. For example, if you have two scalar colored scalar fields in 2 dimensions, and then if you define this vertex operators and you compute this correlation function of vertex operator with this the weak thing, and then with that 2-point function of the Coulomb kind of thing with nearest neighbors only, okay, then you reproduce exactly the thing that you had before. Okay, so you can say, yes.
Once again, this will be all the vertex operators with all the vertex operators. So
yes.
So.
But again, only a few of them, only the ones that are, neighbors will survive. Because of that, here this delta A B. Oh no, sorry, I'm sorry. No, not this ones. I forgot to put the those deltas. I mean, those Kronecker deltas. So now you can say, okay, at least this part of the in this approximation, the dipole approximation, the soft collinear, the infrared structure of SUN gauge theory in the large N limit, it's governed by just a simple theory of free scalars living on the celestial sphere. Okay, so that's what theory is able to capture. Lorenzo Mañea, pretty much the same week, arrived at the same conclusions using the dipole approximation also. I mean, the dipole approximation is the same as the 1 over n, I mean, the large N limit approximation if you keep only the first term in 1 over n. So, okay, this nearest neighbor thing, it's not something new. It's something that people already knew from for a long time. That, for example, you have the amplitude here, and you have the factorization of the soft collinear part in the large N limit. You see this nearest neighbor structure. People knew about this, and you can see, for example, Lance Dixon's review of 2011, where you see that structure appearing in the large N limit. So now the obvious question is like, okay, so what if I go 1 order farther away in the 1 over n expansion? So could this reveal more structure? So I had just a simple theory of just free scalars on the sphere at infinity. If I compute the next correction, could I correct that vanilla Lagrangian that I had? And sorry about this. Okay. So well, I don't know what happened. Even though. Say it again. No. Okay, that's okay. It's not really important. So yeah. All I'm saying is that yeah. Okay, it's not really important. Say it again. Okay, just a little bit there. Okay, so right. Okay, that's so now again. Yeah.
Suppose you have n vertex operator.
Yes.
So the first talks to the second to the third, so on and so forth, and the last one talks to the first one.
I think so. Yeah. I forgot the details, but yeah, you have this cyclic thing noted. Yeah. This is because of the color decomposition thing. Yeah. Yeah. Okay. I'm going to. Yeah. Well, I don't have a definite answer actually. This is like work in progress actually. So that's. So again, let me talk. Let me write down again that original thing. Just the dipole, the one loop, contribution. I'm forgetting about the 3 loops and higher orders. And the state of the art is 4 loops, right? Yeah. For the Caspaloma's dimension matrix.
Caspaloma's dimension is known as 4 loops, but for the non-planar corrections, it's only 3 loops. So the result that you.
Okay. Thank you. Okay, so you can. Okay, let's play the game of seeing, what can you do with this object here. So let's see if it satisfies some kind of differential equations, for example. So do that. Take derivative of this z's, this big z, this big matrix with respect to the coordinates on the celestial sphere, and then you use the some version of the Baker-Campbell-Hausdorff formula. My friends used to call it the Emerson, Lake, and Palmer formula, just for fun. And and now you start computing this commutator. Let me call all this thing. Let me call it A. Okay. So this is what it looks like. And now you see that once you do that, I have this. I did not show it, but okay, I showed it in the next slide. In the 1 over, this is the leading term. These are all 1 over n squared and blah blah blah. So the leading one here, well, not exactly. If you remember, this thing was like when acting on the amplitude, it was some sort of a n times the identity matrix. So there's this is an n times that n, so this is over 1 in n. And these things are of order 1 over n and so on and so forth. So if you can, in that sense, you can think of these things as small corrections to the first one in the 1 over n expansion. So the leading term, if you put everything together, if you look at that, that is exactly the Nishini's homological equation, which is this consistency equation that shows up in the Wessel-Minowitten models in 2 dimensions. So then here you say, okay, great. The theory that lives on the celestial sphere that at least taking into account only the first correction in this Caspar anomalous dimension matrix, the dipole approximation is the Wessel-Minowitten theory. But okay, but not so fast, because again, since we are in the 1 over, the large n limit, again, this thing here gets projected only onto the diagonal part. So it's sort of like a poor version of Nishini's homological, or poor version of Wessel-Minowitten, in which only all the non-abelian structure went away. But okay, that's what you get. For SUN, yes, for SUN. And well, if the Nishini's homological equation here has this geometric, numbers, the level k and the Coxeter number. But if you identify this k over 2n with that, then you get the Nishini's homological equation. Okay, so obviously the next step is to compute 1 over n corrections to this, and the natural question is, okay, if you do this, will you arrive at some consistent deformation of Wessel-Minowitten on the celestial sphere? So yeah, we're working on this with Facu actually now, and yeah, okay. By the way, we were also playing with other limits. For example, you can take yes. Yes, yes. I'm not really an expert, but yeah.
This is larger than W.
This is what?
Sort of large.
Yeah, I think so.
It's
Yeah.
difficult to compare because W is not. In some
Yeah.
So you expect this W still to be embedded here.
The W algebras to be embedded here?
Because this is also infinite dimensional.
Yeah. No, I have no idea. Yeah. That's a very good question, of course, but yeah, I haven't thought about it. Yes.
If you want the full column term, you have to take all the loops, or how do you see it? Because we are only getting the first neighborhood.
Right. So if you take the next one here is going to relax that nearest neighbor thing. That's right. That's right. I mean, again, this comes from here. If you take into account all the the 1 over n corrections up to infinity, then this gluon with partons and everything is going to be everybody against everybody. So that should be reflected in this partition function as well. But we haven't computed it, but it's sort of natural that is the case. Okay. So just playing with other limits, for example, if you take, for example, a limit, and this thing depends on the positions on the celestial sphere, so this positions on the CFT. If you take, for example, other limits like the large or small cross ratio limit, you also get the Nishini's homological equation. And the good thing about that is that now it doesn't get projected into this boring diagonal part. You get the non-abelian structure back again. But the price that you pay for that is because it's only true at that particular limit. So okay. N part. This is for n arbitrary n gluons. Maybe, yeah. Why? What do you have in mind?
Well, because when you solve Newton's homological equation, you can write it down for.
Yes, I agree. Yeah. That's right. Yes. Yeah, no, I haven't I haven't written it down for 4 particles. Yeah, you're right. How much time? I have 5 minutes? Oh my God. Okay. Okay, so I will have zero time to talk about strings. So let me maybe finish. Let me, yeah, okay, with this. So in this celestial business, um, there are a lot of computations at tree level. There's some computations at loop level, and what we wanted to do was to take something that we knew was a formula valid for all loop level. So we look at the BDS formula, which is for the people who maybe have not studied this yet. It was an ansatz proposed by Bern, Dixon, and Smirnov back in 2008, I think. 007, in which the nice thing is, so everybody knew that infrared divergences exponentiate. Weinberg in 64 and 65, wrote the first paper about it. But the surprise was that the hard part also exponentiates. So that was the surprising thing about the BDS formula. So as you can see, this is the formula. So the 4-point MHV amplitude in n equals 4 super-Young mills to all loop order factorizes in this form. So you have the tree level amplitude times this exponential. Here's the infrared exponentiation that people already knew, but this is where all the hard part exponentiates also too. These are a bunch of Vanderstams, S, I plus 1. Again, you see the nearest neighbor structure here also, because the BDS was in the planar limit and larger limit also. So that was already all that nearest neighbor thing, the structure. People knew about it, of course, from long before. Okay. So what if we do the Mellin transform of this thing? What do you get? That's basically, I mean, the celestial amplitude of this. So at the end of the day, you end up with this object here. Okay, you do this 4 integrations. Momentum conservation allows you to collapse 3 of the energies in terms of the 4th one. So at the end of the day, out of the 4 Mellin transform that you have to perform, there's only 1 real one that you have to do. And at the end of the day, after a bunch of changes of variables, this is what you end up with. And you see that this is, so at the end of the day, this is the energy variable, omega. You get log square of something, log square of something, and then have this minus here. So you see that the convergence, this is going to be a Gaussian integral, sort of like a Gaussian integral. You have this factor here, but you see that the convergence of this thing depends crucially on the sign of the cusp anomalous dimension, which is this gamma of A. A is the 't Hooft coupling. So the nice thing is that the cusp anomalous dimension was shown to be strictly positive for all values of the coupling in these papers, Vaso-Konchemsky and also Belinsky, Gutsky, and Konchemsky. So the very existence of the all loop amplitude in this celestial basis or this conformal basis in planar n equals 4 super-Young mill is owed to the positivity of the cusp anomalous dimension. You can see that this is also true for if you do 5 gluons, and again the same thing happens. The cusp anomalous, the positivity of it allows you to write down the full object for 5 gluons. And okay, I will not say anything about strings, I guess. So I mean, I ran out of time, right? You sure? But I mean, I don't know if. Okay, just very quickly. Okay, so I'll do it in. So again, this is what I showed at the beginning. That tree level gravity, blows up. You can see it there, but not for strings. For example, you take the Veneziano amplitude or you take the Virasoro-Shapiro amplitude, and then because of this exponential suppression, these things will converge. For open strings, Gross and Ibañez did the same thing that Gross and Mendel did for this exponentially soft damping at high energies. So that was for closed strings. This is for open strings, but the same thing happens. And also the nice thing is that this is true for all loop perturbatively. I mean, perturbatively in the G in the string coupling. The only difference is that the genus changes just the exponent, but the exponentiation is or that exponential damping is true at all loop order. So okay, I will not say much about this. You can compute that amplitude for open strings. Okay, maybe I'll just skip all this. And one thing that maybe I would like to say is that if you notice this when you compute this amplitude in this conformal basis or celestial basis, as all these names, alpha prime comes out as just a prefactor. So and everybody who has done in some string amplitude knows that if you have an amplitude and you take an expansion and you expand in powers of alpha prime, at leading order you get the field theory amplitude, and then you get corrections to field theory amplitudes. So now you can ask the question, okay, now that you have written the string amplitude on this celestial formalism, but the alpha prime merely comes out as a prefactor outside, how do you take the alpha prime going to infinity limit? So I'm sorry, to zero limit. How do you arrive at the, so this is basically that. So I have a string amplitude in momentum space. I know that I take the alpha prime going to zero limit, I arrive at some field theory amplitude. But for field theory, I can do this Mellin business and get some celestial field theory amplitude. But now, if you go here, you take the string amplitude, you do Mellin, the thing that we did, and now here you don't have alpha prime at your disposal. So how do you get from here to here? That is basically a question that you can ask. And Schieberger and Taylor showed that if you take some sort of Regge limit on the stringy factor only, you recover that. We were looking at that. If you take the limit when R goes to 0, when R was this conformal, cross ratio, this conformal invariant cross ratio, if you take the limit when R goes to 0, you also recover that. But then you can see that this is just a trivial statement of crossing symmetry. The original amplitude is crossing symmetric in the sense that if you exchange S with T, you get an identification of R and 1 over R. So that was the reason why R equals 0, R infinity gives you the same answer. So, okay, we generalize this for loops, for one loop. Okay, I will not say much about it. Let me just show you the last thing. So the full string amplitude in this celestial basis, now it has the thing which is this prefactor here is pretty much dictated by conformal covariance of this two-dimensional object. And now this is the tree-level thing. This is the one-loop correction. And you see here that you get a gamma function of 1 minus beta. Beta has to do with the scaling dimension. So here the thing gets, poles up here, just one order, one integer to the right or left. Okay, okay, I will not say much more about this. So let me just conclude. And here's the mapping that I wanted to mention, the mapping between the string worksheet and the celestial sphere. We have some progress in that. We're working with Stefan Schieberger and Tom Taylor on this, but okay, maybe next time. Okay, thank you.